Problem 2.2. Three rods, one made of silver having K 420 watt per meter Kelvin, second aluminium having K 210 watt per meter Kelvin, and third made of wrought iron K 70 watt per meter Kelvin are coated with a uniform layer of wax all around. The rods are placed vertically in boiling water with 250 mm length of each rod projecting outside. If all rods are 15 mm diameter and 300 mm length and have identical surface coefficient of 12.5 watt per meter Kelvin, work out the ratio of length up to which wax will melt on each rod. So let us draw a schematic for this problem first. As you can see, there are three vertical rods of total length L, and their bottom end is exposed to hot boiling water. Let's say kept in a container, and upper end is exposed to the air having temperature T infinity and convective heat transfer coefficient H. The length of the rods projected outside to the air or surrounding are same and given as x1, x2, x3. All these rods are provided or coated with a wax. So due to heat flow from bottom end towards the upper end of all these three rods, wax will get melted corresponding to their thermal conductivity K1, K2 and K3 respectively. So this entire setup is nothing but a setup similar to used in Ingen Hausz experiment. Let's say surface temperature of the boiling water is Ts and length up to which the wax will melt on each of the rod are L1, L2, L3 respectively, and their thermal conductivities are K1, K2 and K3 respectively. So this is the required schematic for this problem. Now let us enlist all the given things. So x1, x2, x3 are nothing but length of each rod projecting outside, and they are given as 250 mm. Capital L is total length of each rod, 300 mm. Let K1 represent thermal conductivity of silver, given as 420 watt per meter Kelvin. K2 represents thermal conductivity of aluminium, given as 210 watt per meter Kelvin. And K3 represents the thermal conductivity value of wrought iron, given as 70 watt per meter Kelvin. The diameters of each rod are same, that is D1, D2, D3 is equal to 15 mm. Hence, their cross-sectional areas AC1, AC2 and AC3 will also be same. Let's say they are of cylindrical shape, so their cross-sectional area will be pi by 4 d square. And convective heat transfer coefficient of the surrounding fluid is 12.5 watt per meter square Kelvin. After enlisting all the given things, let us make assumptions to have a solution. Assumption number 1 will be one-dimensional steady state heat transfer. Assumption number 2, no thermal contact resistance at the root of the rods. So because of this assumption, temperature of the rod at their root will be equal to temperature of the hot water, that is Ts. Assumption number 3, isotropic and homogeneous material of the fins or rods, that is K1 and K2 and K3 are constant. So thermal conductivities of these rods will be same everywhere. Assumption number 4, uniform fluid properties. So surrounding fluid will have convective heat transfer coefficient value H everywhere. Assumption number 5, no heat transfer due to radiation. And assumption number 6, the rods can be considered as a fins of infinite length. This assumption number 6 is generally derived from the assumption taken in Ingen-Hausz experiment. The rods used in Ingen-Hausz experiments are considered as fins of infinite length. So what you are supposed to find out, we are supposed to calculate ratio of length of each rod up to which wax will melt. That is, we are supposed to calculate L1, L2 and L3 ratio. Now let us do the calculations. So since we have assumed all these rods as fins of infinite length, so for fins of infinite length, temperature distribution can be given as theta x over theta s, that is ratio of excess temperature at any distance x to the ratio of excess temperature at root. This can also be given as Tx minus T infinity over Ts minus T infinity is equal to e to power ml. This this temperature distribution at tip of the fin, that is at x equal to L, where wax melts. So how can I write this? Theta L over theta S is equal to TL minus T infinity over Ts minus T infinity is equal to e to power minus ml. This will be e to power minus mx. If I want to write the expression for temperature at the distance L where wax will get melted, I can write it as T infinity plus Ts minus T infinity over e to power minus ml. Let's say this is equation number 1. Now I can write the expression for this temperature at the point where wax up to which wax will get melted for silver rod, for aluminum rod and for wrought iron rod. So for silver rod, I can write it as TL1 is equal to T infinity. Infinity will be same because all the rods are exposed to the same fluid. TS is also same, e to power minus m1 L1. Let's say equation 2. For aluminum rod, it will be TL2 is equal to T infinity plus Ts minus T infinity e to power minus m2 into L2. And last one is for wrought iron rod, this will be TL3 is equal to T infinity plus Ts minus T infinity e to power minus m3 L3. Now TL1, TL2, now TL1 will be equal to TL2 is equal to TL3. All the rods temperatures are supposed to be same. Hence, equation, sorry, this is equation 3 and this is equation 4. Equation 2, 3 and 4. From equation 2, 3 and 4, what I will get? E to power minus m1 L1 is equal to A to power minus m2 L2 is equal to E to power minus m3 L3. Further, I can write it as m1 L1 is equal to m2 L2 is equal to m3 L3. Here, m is a fin parameter given as HP over KAC. P is the perimeter and AC is the cross-sectional area. So for the M1 will be H into P1 over K1 into AC1 into L1 is equal to H into P2 over K2 into AC2 into L2 is equal to H into P3 over K3 into AC3. Okay. Now as D1 is equal to D2 is equal to D3, hence cross-sectional area of all these three rods will be same. Similarly, length are also same, so their perimeter will also be same. All the rods are of length capital L. So from here, what I will get? L1 is equal to square root of A1. L2 is equal to square root of K2 and L3 is equal L3 over square root of K3. Let's say this is equation number 5. Now let us solve these two equations in combination. So from L1 over A1 is equal to L2 over A2 So L1 over L2 will be K1 over K2 square root. K1 value is given to me as 420 and K2 is 210. So this will be square root of 2. Let us check these values because I could remember them: 420, 210 and 70. So from this, L1 over L2 is 1.414. Similarly, from L2 over L2 over L2 over K2 is equal to L3 over K3. So the ratio of length L2 over L3 will be equal to K2 over K3. K2 is 210, K3 is 70. So it will become square root of 3. So L2 over L3 is equal to 1.732. But these are not the end results. Rather, we are interested in, so L1 into L2 into L3 will be, L1 can be expressed in terms of L2, that is 1.414 L2. L2 can be expressed in terms of L3 and L3 will be L3. So 1.414 L2 can be represented as 1.732 L3 into 1.732 L3 into L3. So ratio will be, if I multiply 1.414 into 1.7.32, I will get 2.45 is to 1.732 is to 1. This becomes L1 is equal to L2 is equal to L3. So this is the answer. So this way you can solve this problem.